When you're troubleshooting an AC motor controller, sequencing charts can be a valuable tool in determining how the controller is supposed to operate. They can also be helpful in determining the positions that switch contacts may be in during a malfunction, which may be a clue as to what went wrong. Take a moment now to check your understanding of diagrams and charts used with AC motor controllers by trying a question. In this part, we'll look at procedures that you can use when you have to locate the cause of an AC motor controller malfunction. In other words, when you're troubleshooting. A typical troubleshooting procedure can be broken down into a series of steps that you can follow. First, you need to know or understand how the controller normally operates. The second step is to question or investigate how the controller was actually operating during the malfunction. After you investigate, you need to evaluate or attempt to define the problem by comparing the controller's normal operation with how it's operating during the malfunction. The next step is to inspect the controller and examine its components. And then, after the cause has been identified, you should make the necessary repairs. Finally, after you've made the repairs, you should test the controller to make sure that it is operating correctly. Let's look at the steps in this procedure one at a time and see what can be involved. When you begin troubleshooting, it's important for you to fully understand how the controller should normally operate. If you don't know how the controller is supposed to operate, you can't effectively identify the symptoms of a problem and determine its possible causes. Many sources of information are available to help you determine how a controller normally operates. You may be familiar with the controller's operation from your own experience. If that's the case, you can draw on that experience to make troubleshooting less complicated. The person who operates the controller can be an excellent source of information as well. From working with the controller on a daily basis, that person should be quite familiar with its normal operation. Plant supervisors can be another good source. Many of them have worked their way up through the ranks, and they often know a lot about the normal operation of the facility's equipment. Schematic diagrams can help you identify the controller's components and how they are electrically connected. Using a schematic diagram to trace the current paths through the controller is one way to determine how the controller is supposed to work. Other sources of information include system description manuals and technical manuals. System description manuals typically describe what a system is, what components it contains, how the system and its components usually operate, and where each part of the system is located. And manufacturers sometimes supply technical manuals for their motor controllers. These manuals describe normal controller operation and provide other pertinent information. Once you know how the controller should operate, you can investigate how the controller is actually operating during the malfunction. To do this, you have to identify the symptoms of the problem and then decide what to do about them. The operator who reported the problem is often the best source of information about the problem's symptoms. This person can most likely give you a clear description of what's going on. If this person is not available, you might be able to talk to the supervisor who received the trouble report, or read the trouble report yourself. In some cases, you may need to test run the controller so that you can observe the malfunction firsthand. But test running a controller can sometimes further complicate the problem. For example, if one of the symptoms was the smell of burnt insulation or smoke, a test run could further damage the insulation or cause a fire in the controller, so the situation should be evaluated before a test run is made. And whenever you do make a test run, make sure that all applicable procedures are followed. After you've investigated, you need to evaluate. In other words, you need to compare how the controller operates normally with how it operates during the malfunction. One of the best ways to evaluate is to list all the possible causes of the problem and then systematically examine each possibility. This way, you can narrow down the possible causes or pinpoint the actual cause. The controller's schematic diagram is generally used during the evaluation process. The schematic shows you what the components are, how they're supposed to operate, and how current flows through the controller. With the schematic, you can compare what is happening with what is supposed to happen. That way, you can eliminate any components that are working correctly. After the possible causes of the controller malfunction have been narrowed down, the components that have not been eliminated should be carefully inspected. You can use the motor controller's wiring diagram as a guide to locate each component. During an inspection, it's important to follow all applicable safety precautions. You can usually begin your inspection by using your senses of sight, touch, and smell to thoroughly examine the controller. You should look for anything out of the ordinary, such as dirt, burnt insulation, broken wires, or loose parts. An unusual smell may indicate burnt insulation, and a hot spot may indicate overheating. If the visual inspection does not result in finding the cause of the problem, the next step, generally, is to take electrical test measurements. 3 common faults you can test for are grounds, opens, and shorts. Test procedures for each of these problems are covered in some detail in this unit in the topic called Troubleshooting. Once the cause of the controller problem has been identified, the next step is to make the necessary repairs. Repairing an AC motor controller often includes replacing components that are malfunctioning. When replacements are made, the new components must be the same size and rating as the original components. If the cause of the malfunction is defective or damaged contacts, you should replace both the movable and stationary contacts at the same time so that they will make good clean contact when they're closed. After the repairs are made, the last troubleshooting task is to test the controller to make sure that it is operating correctly. To test a controller, you should operate it through all of its different operating modes to make sure that everything is operating the way it should and that there are no other signs of problems. While you're testing, pay special attention to any replaced or repaired components to ensure that they are operating correctly. Also, while you're testing, you may need to make adjustments to the controller and reset devices that require resetting. For example, after a pressure switch or a float switch is repaired or replaced, you may need to set the operating levels for the switch. Sometimes, several malfunctions occur in a controller at the same time. After each malfunction is corrected, other problems that are present and undetected will make themselves known during the test run. The new symptoms can then be evaluated, inspected, repaired, and tested. Take a moment now to check your understanding of how a malfunction in an AC motor controller can be identified and solved. In this topic, we introduced some diagrams, charts, and procedures that you can use to maintain and troubleshoot AC motor controllers. Try some practice questions now that relate to this material. In this part, we'll look at how you can troubleshoot an energized AC motor controller. Basically, there's one major reason for troubleshooting an AC motor controller while it is energized. Shutting down a controller can sometimes interfere with the operation of other equipment in the facility. For example, when 2 separate control systems receive their power through the same power supply breaker, opening the power supply breaker de-energizes both control systems, and that could be a problem. In a case like this, an electrician may first attempt to locate the problem by testing the malfunctioning controller while it is energized. It's important to remember that you should test an energized controller only if the symptoms of the malfunction indicate that testing will not further complicate the controller's problem. For example, symptoms such as the smell of burnt insulation, sparks, smoke, or glowing wires are warning signals that you should not test the controller while it's energized. When you're working on an energized controller, you must follow all applicable safety rules, including the use of safety glasses and the properly rated leather-covered rubber safety gloves. The 3 electrical problems that can occur in a controller are grounds, shorts, and opens. However, an energized controller is not usually tested for grounds and shorts. Although one ground in a controller circuit is measurable, it has little or no effect. In fact, some controllers are intentionally grounded. When a short occurs, the controller's fuses or circuit breaker open and the controller is de-energized. For this reason, energized controllers are not normally tested for grounds and shorts, but they are tested for opens. One way to test an energized controller for opens is to test for voltage drops across various parts of the controller's circuits. Generally, If an open exists in a circuit, there will be a voltage drop in that part of the circuit. Let's follow an electrician as he uses a voltage tester to check for an open in an energized motor controller. In this example, the electrician has already evaluated the symptoms of a controller malfunction and has narrowed down the possible causes of the problem with the aid of a schematic diagram. He thinks that the problem is probably in the controller's maintaining contacts or in the wires leading to the maintaining contacts. This is a simplified schematic of the motor controller's control circuit. It includes the stop button, the start button and its maintaining contacts, and the M coil. This symbol, a circle with the letter V inside, represents the voltage tester. The lines connected to it represent the test probes. One test probe is placed at the electrical connection point on one side of the maintaining contacts, and the other probe is placed at the electrical connection point on the other side. The maintaining contacts are normally open, so current flows from line lead L1 through the circuit and the voltage tester to line lead L2. If the wires leading to the maintaining contacts are good, the voltage reading should indicate full line voltage, and it does. Since the wires leading to the maintaining contacts are good, the malfunction has to be caused by a problem with the maintaining contacts themselves. Now let's look at another example that's a little more involved. We'll use a simplified schematic of a controller's control circuit to see how you can troubleshoot an energized controller that has a malfunctioning stop button. This simplified diagram represents the controller's control circuit. The malfunctioning stop button is represented in the open position. The electrical connection points shown on the diagram are numbered from 1 through 8 for ease of reference. In this example, the only identifiable symptom of the controller malfunction is that the motor will not start. One way to isolate the cause of the malfunction is to take voltage readings across each component in the control circuit. The first step is to verify that power is available from line lead L1 to line lead L2. The electrician uses a voltage tester to make the test. The meter indicates full line voltage, which means that power is available. The next step is to place one of the probes on L1 and the other on electrical connection point 2. If the circuit from L2 through the M coil is complete, voltage will reach connection point 2, and the voltage tester will indicate full line voltage. When the electrician conducts the test, the voltage tester gives a full line voltage reading. Voltage is reaching connection point 2, so the M coil and the wiring from the M coil to L2 are good. The power supply, the M coil, and the wiring from the M coil to L2 can be eliminated as the cause of the problem. The next test is made from L1 to connection point 4, and the voltage tester again indicates full line voltage. This means that there is a complete voltage path from L2 to connection point 4, so the wiring and components from point 4 to L2 can also be eliminated as a cause of the problem. The next test is made from connection point 4 to connection point 8. Again, the reading is good, so the electrician knows that the wires from L1 to connection point 8 are okay. At this point, the wiring and components from connection point 4 to line lead L2 and from connection point 8 to line lead L1 can be eliminated as the cause of the problem. This means that the open must exist somewhere between connection point 8 and connection point 4. So the final test is made from connection point 7 on the other side of the stop button to connection point 4. The voltage tester reading for this test is 0, which means that voltage is unable to reach connection point 7. This reading indicates that the stop button is malfunctioning and is, in effect, open. The problem is now isolated and it can be corrected.